Hi, hello friends. Welcome to Indian Tech Guru for you. In this video, let us learn about N-Queen's problem using backtracking. So first of all, what is meant by backtracking? Backtracking is a method in which we are going to try to solve the problem, and if at all there is no way to solve the problem by using a particular path, then come back to the original path and track from there. So until unless we get the solution, keep going. This approach is called as backtracking, and we're going to solve the n-queens problem using backtracking. So first of all, let me take the four queen problem, and try to solve this particular problem. So in four queen problem, let us assume that there are four queens q1, q2, q3, and q4. Four queens are there, and these four queens must be placed in this particular chessboard, which contains 16 locations, and we need to make sure that no no two queens shall be in the same row or same column or same diagonal. So as far as chess rules are concerned, queen can go either straight or diagonal or vertical. So it can move either horizontal or vertical or diagonal. That's why we need to make sure that other queen should not be there either in the horizontal or vertical or diagonal way. So we need to make sure that these three rules must be applied. So then only we can easily solve the problem. Okay. So first of all, let me restrict these particular queens in such a way that q1 must be placed in row 1, q2 must be placed in row 2, q3 must be placed in row 3, and q4 must be placed in row 4, so that we can reduce the number of iterations that are needed to solve this particular problem. And we are not making any conclusions regarding the column as well as diagonal, but we are making conclusions that q1 must reside in row 1, q2 must reside in row 2, q3 in row 3, and q4 in row 4. So now let us solve this particular problem using backtracking technique. So let me have some space here because we are going to get a large tree for backtracking purpose. So the tree which is resulting from this particular solution is called as a state space tree. State space tree. So first of all, let us start with the location, and then assume that q1 is placed in first column. So whenever I say q1 is equal to 1, it means that it is placed in first column. So already the rows are fixed, so we need not to worry about the rows. But now the column must be fixed. So q1 equal to 1 means q1 is placed in first column here, q1. And now there are three different locations in which we can place q2. Either we can place q2 in second column or third column or fourth column. First of all, let me try to place in second column. So that is q2 is equal to 2 represents that q2 is placed in second column. However, if you place q2 here, then it will place it diagonally, so it violates the rule. So that's why this particular tracking is not acceptable. So that's why come back to the original location and then track in another way, that is place q2 in third column. So you can place q2 here, q2. So is there any problem now? There is no problem because q1 and q2 are not in the same row, same column, as well as same diagonal. So now we need to track the location for q3. So already first location is over, third location is given for q2. So that's why we could not actually store q3 either in first location or third location. We need to consider the remaining locations. So if you place in first location or third location, then it will be in the same column. So that's why we can avoid that straight away. And now what are the two leftover locations? 2 and 4. 1 and 3 are over, 2 and 4. So let me try to place q3 in second location. q3 in second location. So if I place q3 here, then diagonally it is not possible. So there is a clash diagonal in diagonal. That is why this path is wrong. So what else? 1 is over, 3 is over, 2 is over. The remaining location is q3 is equal to 4. If I place q3 in fourth location, so then also diagonally it is not possible. So that's why it is also not acceptable. So because these two are not acceptable, so this path is not acceptable. And now we need to go for another path, that is, so we are not placing uh, q2 in third location, so this is cancelled. And now try placing q2 in fourth location. So q2 here, so it is acceptable. And then we need to track for q3 and q4. So now let me assume that q3 is placed in 1 and 4 is over, is placed in second location. So q3 here, it is acceptable because there is no problem uh, either in row or column or diagonal. So now what is left over? 1, q1 in 1, q2 in 4, q3 in 2, 1, 4, 2 over. So now try to place q4 in third location. However, if I try to place q4 in third location here, then diagonally there is a clash. So that's why it is not acceptable. Because it is not acceptable, so we cannot place q3 in 2. So ultimately all the combinations of q1 equal to 1 over. So that's why it is not possible by placing q1 in first location to solve this particular problem. So then what we need to do? We need to make sure that now q1 is placed in second location, and we need to try from the scratch. So I will be removing these values. Now, so let us start with the q1 in location 2, column 2, q1 here. And whenever q1 in location 2, then what are the leftover places? The leftover places are q2 in location 1. However, it is not possible diagonally to place q2 in location 1. So it is not possible. Then q2 in location 3, it is also not possible because diagonally it is not acceptable. And finally q2 in location 4 it is acceptable. So because either row wise or column wise or diagonal wise, there is no problem. So once Q2 is placed in 4, then second location is over, fourth location is over. What are the remaining locations? 3 and 1, 1 and 3. So try to place Q3 in first location. So if I place Q3 here, there is no issue either in row wise or column wise or diagonal wise. Now 2 is over, 4 is over, 1 is over. So now I try to place Q4. What is the remaining location? Third location. So if I place Q4 in third column, then Q4 in third column, then there is no issue at all, either in row wise or column wise or diagonal wise. So this is the final solution we got. So Q1 is equal to 2, that is place Q1 in second location, Q2 equal to 4, that is place Q2 in fourth location, Q3 is equal to 1, that is place Q3 in first location, and Q4 is equal to 3, that is place Q4 in third location. So however, in case of backtracking, there is no rule that we are going to get only one solution. We may get more than one solution also using backtracking. So however, we may consider one among the several solutions. So for example, here, if you start from Q1 is equal to 3, from Q1 is equal to 3, so let us track and see that whether solution available or not. So starting from Q1 equal to 3, what does it mean? Place Q1 in third column, and then we need to place try to place Q2 in first location. Is it acceptable? Yes, there is no issue. And what are the leftover after 3, 1, 2 and 4? Try to place Q3 in second location. It is not possible diagonally. There is a clash. So not possible. Next, try to place Q3 in fourth location because it is the leftover. So Q3 in fourth location, there is no issue. And what is the remaining? 3, 1, 4 and finally 2. Q4 in second location, we can place Q4 in second location, there is no issue. So now the solution is so place Q1 in third column, Q2 in first column, Q3 in fourth column and Q4 in second column. So this is also one of the other solution. So the first solution we got is 2, 4, 1 and 3. The second solution we got is 3, 1, 4 and 2. So now you can observe that there are more than one solution for solving the any problem using backtracking. However, so we shall consider one of the solutions that are possible while solving the problem. So likewise, we can solve an 8 queen problem using the same methodology. 8 queens problem. So 8 queens problem, for solving 8 queens problem, so there will be 8 queens from Q1 to Q8, and we need to consider a chessboard of 8 rows and 8 columns. 1, 2, 3, 4, 5, 6, 7 and 8. So 1, 2, 3, 4, 5, 6, 7 and 8. So we need to consider 8 by 8 chessboard. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So as usual, we are going to solve this problem as we have seen in the 4 queens problem. So starting from Q1 and draw the state space tree for Q1. So if at all there is no solution available, if you start from Q1, then start trying from Q2, and then Q2 in location 2, Q1 in location 2, and then Q1 in location 3, and then Q1 in location 4, something like that. So let me start from Q1 from location 4. So assume Q1 is placed in location 4. So Q1 is equal to 4. So Q1 is placed in fourth column, and then we can place Q2 either in first column, second column, third column, any of these columns. So let me assume that Q2 is placed in first column, Q2 here. So and then now place Q3, in second location. However, if you place Q3 in second location, diagonally there is a clash. So this is not acceptable. Now try to place in third location. If you try to place in third location, there is a clash, diagonal clash. So it is also not possible. Q3 is equal to 3, also not possible. So 4 already over. Next Q3 is equal to 5, also not possible. So because diagonally there is a clash. So Q3 is equal to 6 is possible. So if you place uh, Q if you place Q3 in sixth column, so then there will not be any clash. Even in 5 there is no clash. So we can place Q3 in 5. This is not needed. So you can place Q3 in fifth location. So likewise, we are going to track the entire locations, and whenever there is no possibility, then come back to the previous path and trace from there. Like this, we can solve the 8 queens problem also. So hope you understand the logic. That's all for now.